Welcome back. So, partial derivatives are just like normal derivatives, except these are for multivariable functions, while derivatives are for single variable functions. So, again, let's start with what we already know, that is, derivatives. Like I said, are for single variable functions. So, let's take a single variable function y equals to f of x, where x is the independent variable and x belongs to R. Since it has one variable, we directly differentiate it with respect to x, which is df by dx. And let's say we're differentiating at x equals to a. So this will be equal to f dash a. And f dash a can be also written as limit x tends to a, f of x plus a minus f of x by a. Let's put that aside. Now, for partial derivatives, like I said, they are for multivariable functions. So let's take a function z equals to f of x comma y, where x and y are the independent variables and x and y belong to R. That is the real numbers. Since this function has two variables, we can't directly differentiate it with both the variables at the same time. So we can differentiate the equation with one variable at a time. Since we're differentiating it with respect to x, we can write it as dou z by dou x or dou f by dou x, f of x, x comma y, and dx, subscript x. Now, dou z by dou x is also equals to limit x tends to 0, f of x plus dou x comma y minus f of x comma y by dou x. Now, how did we get this formula? So if you look at normal derivatives, this formula and this formula look pretty similar. Here we're giving a small nudge of value a in the x direction. So that's why we get f of x plus a minus fx by a. While here we are giving a nudge in the x direction of a small value dou x. And since it's a very small value, it almost tends to 0. And we're not giving any nudge in the y direction. That's why we're not adding any quantity here. So that's how we got this formula. Now we've differentiated it here with respect to x. We can also similarly differentiate it with respect to y. And then we'd get dou z by dou y, dou f by dou y, dou fy. And then we get dou z by dou y, dou f by dou y, and so on. So dou z by dou y, similarly we get limit dy tends to 0, f of x comma y plus dou y minus f of x comma y by dou y. Now these are called as first order partial derivatives. This can be written as f of x and this can be written as f of y. Now f of x and f of y can be further partially differentiated with the same variables, and those will be called as second order derivatives. And those will be called as second order partial derivatives. And they are as follows. This can also be written as f of xx, and this would be f of yx. So we're writing this one first and then we write this in the subscript. And this would be f of, xy, and this is f of yy. And usually in all the ordinary cases, these both tend to be equal. Sometimes these are also given a different notation. So f of x, that is dou z by dou x, is given as p. F of y, that is dou z by dou y, is given as q. This is given as r. This is given as s, and this is given as t. It's better to keep these notations in mind as well, because sometimes in your questions, they can either directly ask derivative with respect to x like dou z by dou x, or they can ask find p, q, r, s, and t. Keep that in mind. Now if a function has more than two variables, we can do them also in the same way. And it is also observed that for a function of two variables, it has two first order equations and 2 square of second order equations and 2 cube of third order equations, and so on. You can observe this pattern for more variables as well. Now let's see if this satisfies for this. We have two first order derivatives, that is p and q, and second order derivatives we have 4. 1, 2, 3, 4. And if you do third order, you're gonna get 8. So maybe check that out later. Now let's do an exercise problem to get a hang of it. So this is the problem given. This is our function, and they asked us to show that dou square z by dou x square is equals to a into dou square z by dou y square. So first we find out dou z by dou x. Now we're differentiating it with respect to x, so we take y as constant and we do the derivation. Let's have some formulas in mind here. We already know these. So if we differentiate tan x with respect to x, we get secant square x. And if we differentiate x bar n with respect to x, we get n into x bar n minus 1. And if we differentiate secant x with respect to x, we get secant x tan x. So dou z by dou x here is equals to secant square y plus ax. Y is constant, so we again derivate ax and we get a minus 3 by 2 y minus ax 1 by 2. And again minus ax we derivated and we get minus a. Now let's derivate this again with respect to x. So dou square z by dou x square is equals to 2 secant y plus ax, and secant derivative is secant x tan x, right? Secant x tan x, and again we have to derivate this part, so ax derivative is again a, and we already have another a here. Let's write it here, okay? And now let's derivate this part, and we get minus 3 by 2 1 by 2 y minus ax minus 1 by 2. We already have a minus a, let's put it here, and we derivate this part again, so we get minus a. So this is equals to, let's take a square common, and we get a square 2 secant y plus ax, 2 secant square y plus ax tan y plus ax minus 3 by 4 y minus ax to the power minus 1 by 2. Let's take this as equation 1. Now let's differentiate this equation with respect to y. So dou z by dou y is equals to secant square y plus ax, and when we differentiate this, we're taking x as constant, and so y, if you differentiate it with respect to y, it's 1 minus 3 by 2 y minus ax 1 by 2, and this will again be 1. Let's differentiate it again with respect to y, and we get 2 secant y plus ax, and secant y derivative is secant y tan y, and this is what we get. Now let's differentiate this part with respect to y, and we'd get y minus ax to the power 1 by 2. And we can write this as 2 secant square y plus ax into tan y plus ax minus 3 by 2, okay, this is 3 by 4, y minus ax to the power 1 by 2. And we can take it as equation 2. If we compare equations 1 and 2, we get that d square z by dx square is equals to a square of d square z by dy square, because this whole term and this whole term are same, so you substitute this over here. And let's go on with the next topic.